This section examines electrical functions in EFI. In the electrical system, detecting elements sense engine operating conditions and relay this information in the form of electrical signals to the Electronic Control Unit, or ECU. The ECU is a small computer, programmed with the operating characteristics of each individual application. This information is stored in its memory. The control unit processes input signals to determine the amount of fuel required by the engine at that instant. It then grounds the injection valve circuit to open the solenoid-operated injection valves. The length of time injectors stay open in milliseconds determines how much fuel is injected. A basic EFI system needs input signals on ignition switch operation, engine cranking, the amount of air entering the engine coolant temperature, throttle position and engine speed, and battery voltage. The varying data received from all of these inputs allows the ECU to arrive at its injection setting. This vehicle began from a cold start and has been running only a short time. It is now operating in top gear with a light throttle only. What influences its fuel requirements? A relatively small volume of air is entering the engine. The throttle position is associated with economy or cruising conditions. Engine speed is in the low to mid-range. Coolant temperature is still below normal. These factors combined produce a fuel setting. It is less than if the throttle were opened suddenly for acceleration or to overcome increased load. However, it is more than it would be if coolant temperature were at its normal level. The varying signals can be supplied by variable resistors, by switch contacts, by voltage pulses from the ignition system, or by sensors. An airflow meter varies its signal by the deflection of a vane as air enters the engine. Deflecting the vane moves contacts across a potentiometer to signal its position and thus the amount of air entering the system. The temperature sensor uses material with a negative temperature coefficient of resistance. Its resistance is high when it's cold, but it falls as its temperature rises. It's called a thermistor. This is the opposite of a normal resistor, which increases its resistance as temperature rises. The coolant temperature sensor is immersed in coolant in the cylinder head. The air temperature sensor is in the air intake at the airflow meter or in the manifold. Throttle position can be signaled by a potentiometer attached to the throttle shaft. It provides a continuous varying signal through the entire range of throttle position. Throttle position can also be signaled by a contact-type switch, but it signals the idle and fully open positions only. Engine speed can be detected by a connection from the ignition system primary circuit or by a pulse generator type sensor on the crankshaft. The pulses are computed by the control unit into an engine RPM figure. They can also be used to trigger the injectors. In multi-point injection, the injectors can all be triggered at the same time. This is called simultaneous injection, and the injectors operate twice per cycle. That's once each crankshaft revolution, each time delivering half the fuel for the cycle. In a six-cylinder engine, the injectors are triggered on every third ignition pulse. In throttle body systems, the central injector is normally triggered on every ignition pulse. However, if there are two injectors, alternate triggering may be used. At idling speeds, the frequency may be less to provide finer control. The actual operating time of the injectors depends very much on battery voltage. The response time to lift the injector needle to the fully open position is about 1 millisecond. If battery voltage is low, this response time takes longer and the engine receives less fuel. The ECU can compensate for this delay in opening time by extending the duration of the injection pulse. In more sophisticated engine management systems, the control unit can control additional functions such as ignition timing, injection modes, idle speed, cooling fans and fuel pump operation. To do this, however, more inputs are needed. To control ignition timing, some systems replace the distributor with a direct fire ignition system. Between one ignition point and the next, the ECU calculates when the ignition point will occur. It then triggers the ignition accordingly. Ignition can be varied according to load, speed, coolant temperature, cranking speed and battery voltage. Identifying number 1 cylinder and the camshaft position allows different injection modes to be used. Sequential injection means injection occurs in the sequence of the firing order. Each injector opens once only in each cycle to deliver the fuel needed. Added load placed on the engine during idle can be compensated for by increasing the passageway of an idle speed control device. This lets more air bypass the throttle plate. This air has been measured by the airflow meter, so extra fuel is metered to maintain the same air-fuel ratio. The extra mixture thus delivered increases engine torque and maintains idle speed. For efficient operation of the catalytic converter, the mixture ratio must be maintained close to the stoichiometric ratio, 14.7 parts of air to 1 part of fuel. Efficiency of combustion can be monitored by measuring the percentage of oxygen in the exhaust gas. A high percentage may mean the mixture entering the cylinder is too lean. The oxygen sensor in the exhaust manifold or in the engine pipe tells the ECU how much oxygen is in the exhaust gas. The ECU then varies injector opening time to achieve a correct mixture ratio. Feedback also lets fuel settings change as components age. This is called adaptive learning. The ECU memorizes its fuel settings for different operating conditions and stores them for future use. If a fault occurs in a component or part of a system, a fault code can be displayed on the check engine lamp in front of the driver. Alternatively, a scanning tool can be connected to a diagnostic terminal and information on the fault can be analyzed. Although most injectors operate at the nominal battery voltage of 12 volts, many sensors have a reference voltage of 5 volts. This is done by a voltage regulator in the control unit. It gives more accurate signaling, as fluctuations due to changes in battery voltage do not occur.